Hello again, everyone. Here I wanted to talk about applications of right-angle trigonometry. So basically I'm going to be talking really lightly about trigonometry in a very practical sense. So we're not going to get into the details that you would normally see in a trigonometry class, but at least for our purposes, what we need. So here, the intro of the classic three trig ratios are sine, cosine, and tangent, given a right triangle with the sides y, x, and r with an angle theta. It's a Greek letter theta. Sine of theta is y over r, cosine of theta is x over r, and tangent of theta is y over x. Now, commonly people remember this as opposite side, adjacent side, and hypotenuse of the right triangle. Now, of course, it has to be a right triangle. That's why it's called right angle trigonometry after all. And notice this is really just opposite over hypotenuse. Cosine is adjacent over hypotenuse. And then finally, tangent is, opposite over adjacent. So very often people, to remember this, remember the acronym SOHCAHTOA, which you may or may not have heard before. And that's just a memory scheme, basically. There's a funny acronym I've learned recently. It's some old hippie caught another hippie tripping on acid. So if you want to use that, I think that's a kind of fun way to remember it. And also, for right-angle trigonometry specifically, the angle itself is going to be in between 0 and 90 degrees. In fact, it's not going to be equal in our cases because otherwise you wouldn't actually have a right triangle. So that's something to think about. Now in trigonometry, we actually extend this definition and go beyond this. In fact, you can find sine, cosine, tangent for any angle you can think of, even negative angles. And we also go and talk about a different unit of angles, which is called radians, which is more of a natural unit of a measure for angles. But again, here we're not going to really talk about those details. We're going to kind of sweep those under the rug, if you will. So now first, before we actually begin the problem solving, I want to kind of show you some tools. And let me kind of separate things here. Well, also before I move on, something that's kind of something that people normally know going into this, but I'll just write it over here, I guess, is just recall Pythagorean theorem. So the Pythagorean theorem, of course, is applicable. It's relatable here because we have a right triangle. And in this particular instance, using these notations for the sides of the right triangle, we'll have x squared plus y squared is equal to r squared. So for any right triangle, you can do that. You can square one non-hypotenuse side added to the other non-hypotenuse side squared, and their sum should be the square of the hypotenuse side. Good. Okay, so now back to these tools. I call them maneuvers, so the proportion maneuvers. Proportion, by the way, is when you have a fraction equal to a fraction. For our cases, we'll be seeing a number equals a fraction, which a number, if you think about it, is still like itself over 1, so you can still think of it satisfying this. And we have these three equivalences. So notice here, these two switch, so this is known as a swap maneuver. Here, we're cross multiplying, so this is cross multiplying. People normally have seen this one before. Maybe not the swap so much, but it's something you can definitely do. In fact, we'll kind of see later on, there's actually a swap for subtraction as well. But for right now, let's just kind of stay focused. And here what we're doing is reciprocating both sides. So this is reciprocating. And if you want, you can verify these on your own. It's not really difficult. Really, it's just algebra manipulation. But it makes things go a lot quicker if we know these ahead of time. So here, in this example, I didn't label the directions, but I want to find the unknowns, x and r. All we know is that this angle is 30 degrees in this right triangle. And we're going to use our calculator to help us find sine, cosine, and tangent of any angle, which is something I should have mentioned before. Otherwise, in a trigonometry class, you would know sine, cosine, and tangent of 30 degrees. I may mention what that is, but I'll just use a calculator. So let's first set it up. Now, it depends obviously what we want to find. Now, in this case, we want to find both of them. So in fact, we may actually incorporate the Pythagorean theorem, but let's just say we want to find x first. So if I want to find x, ignore r. Ignoring r, if I only want to find x, which of these trig functions involves this side and this side? And of course, if you look at the labeling here, this is y and x. And the only one that involves both y and x is tangent. So we're going to take tangent of the angle, tangent of 30. So you know what, just to kind of help us out, I very often omit the parentheses, but you could write parentheses here just to remind us that tangent, cosine, and sine are both, not both, but are all functions of the angle. And let me lower this a little bit so we have more space. So I have tangent of 30 degrees is equal to opposite over adjacent, so that's 20 over x. Now remember, we want to solve for x, so we can perform a swap here. So if we swap, then we get x is equal to 20 over tangent of 30. And notice here I'm not writing the parentheses. So now I'm going to use my calculator. I'm using a TI-83 Plus, by the way. Make sure you're in degree mode. So what that entails is just to press mode. And you can see right here I'm in degree mode for the third line. And if you're in radians, just arrow down and then select degrees. So now I'm going to type in 20 divided by tangent of 30 degrees, just like this. Great, there's not too much reflection there. And I got about 34.64. So I'm at around 34.64, and that's x. I'll box this. Now I didn't specify as far as what to round to. Normally I'll try my best to specify what I want you to round to, but again, these are applications. We want to be kind of practical. And of course, we could be as accurate as we want, but I think this is accurate enough as far as measuring goes. And really, these things represent lengths, and you'll be measuring with these, so I think this is fine. Okay, I did mention that I may have said the accurate, or I guess exact value of tangent of 30 degrees. And I'll just say it, it's radical 3 over 3. So if you divide by radical 3 over 3, that would be multiplying by the reciprocal, which is 3 over radical 3. So that would be 60 over radical 3. So if you want to verify on your own, I'll just do it real quick. 60 over the square root of 3 should also give you 34.64, and I just checked and it does. And if you want to find r, how can we find r? We can find r two ways now. Well, actually, three ways, really. We can either use one of these functions. In fact, there are two we can use. Because since we want to find r, it's a hypotenuse. There are two that involve the hypotenuse, sine or cosine. Now, if we did not know x ahead of time and we found r first, we would have no choice but to use sine, because sine would involve this side over that side. But now that we know x, we have the option to use cosine. So those are two of the three options. The third option now is to use the Pythagorean theorem to find r, because we know x and y in this case. In fact, I'm going to do that here, just to show you. So using Pythagorean theorem, we have x squared, which is 34.64 now, squared, plus y squared, which is 20 squared, equals r squared. So that means to find r, we have to square root this result. So let me just write r is approximately equal to, well, let me just write equals. I guess it is approximate because we're approximating x, but the approximate and equality symbol for practical uses will be kind of the same. Let's just see what this is using my calculator real quick. So I got 34.64 squared plus 20 squared is 400, so it's almost 1600. So it's 1599.93 if you round. And then taking the square root of this will be about 400, not 400, but about 40, because the square root of 1600 is 40. So this is approximately 40. It's like 39.99. So I'm just going to say approximately 40. And in fact, the reason being here is because, let's say we took, so let's say we took sine. Sine of 30 degrees actually has an exact value of 1/2, believe it or not. And notice, if sine of 30 is equal to 20 over r, writing it over here, and if you know the exact value, this is where that kind of comes into play. You get 1/2 is equal to 20 over r. So notice if you cross multiply, you'll just get r is equal to 40 right away. Exact, no messing with approximations. So that's really nice, using the fact that we know an exact value of sine of 30 degrees. Let me just write r is equal to 40. But again, we won't really be using those exact results from trigonometry, just because, to be quite honest, in a lot of the applications we'll be seeing, the angles won't be this nice. In fact, very often we'll be seeing, let's say like 32 degrees or 65 or 67, 75, something like that, where you actually don't know the exact value of any of these trig ratios. Okay, so I think I've spoken enough here for this one example. We're going to do a few more examples involving this, and then finally we're going to take a look at a different type of example where we'll be solving for the actual angle using what are called trig inverse, or I guess inverse trig functions. So let's see those examples right now. All right, so here's a very typical example that we'll see that I was kind of building up to from the previous example. So let's read. It says, support line from the horizontal, so from the floor, extends to the top of a 65-foot pole at an angle of 42 degrees. How far away from the pole must the support line be anchored? So again, pretty practical application of trigonometry. Let me draw a picture here. So we have horizontal floor, we have a pole, vertical pole that is 65 feet, standing like this, and then we have some support line that goes to the ground at an angle of 42 degrees. Great. Now, let's just, again, it's supposed to be a pretty practical example. So let's just say you're tasked with setting this situation up, actually installing the support line. So if you have to have this angle, let's say that's a standard for whatever reason, can you find out how far away from the pole you have to be? It's kind of what this question's asking. So can we find x? Now, of course, it's going to be measured in feet because the only other, measurement here we have is feet, of course. The only measurement we have is the feet. And it's given here that this is a right angle because the floor is horizontal. We're assuming the pole is completely vertical at a 90-degree angle. So we actually have a right triangle. And we want to use trigonometry to find x, to find the unknown. Now, think about what I said earlier. We have this side length and we have this side length involved. This one's known, this one's not known, but still we have these two. Now, which of the trig functions that we saw, sine, cosine, or tangent, can we use to solve for x in this case? And it is tangent, because we have opposite and adjacent of this angle. So we can say the tangent of the angle, 42 degrees, is equal to the opposite side, 65, divided by the adjacent side, x. Notice here I'm not writing feet. I know x is going to be in feet, so I'll write that at the very end. I'll perform a swap here. To get x by itself, x is going to be 65 over tangent of 42 degrees. Again, remember that your calculator must be in degree mode, or else this won't work. So I'm just going to type this up real quick. 65 divided by tangent of 42, and I get about 72 point, it rounds to, let's say, 72.2 feet. And in fact, if you want to be accurate, I'll kind of show you how to be more accurate here. So this 0.2, I'll tell you what it really is. So in the calculator, I'm getting exactly this. 72.1898, and I think that'll be accurate enough. Now this remaining part here, what I'm going to do is I'm going to say this is in feet, of course, and this is less than a foot. So I can actually convert this, if you want to, in inches. And since this part here is in feet already, how do we convert feet to inches? Well, remember that there are 12 inches in 1 foot. So I'm going to multiply this remaining decimal part by 12. So on my calculator, I'll write minus 72, and it'll just give me this 0.1898 part, just to remain super accurate. Then if we press times 12, we get 2.27. So if you want, you can say or 72 feet and 2.27 inches. It actually rounds to 2.8 because it's 277 inches. So if you want to, I guess, be pretty accurate as far as getting the job done, you can say this is close to 2.5. So I know that's rounding down, which you can go a little bit beyond 2.5. But again, the reason why I'm using 2.5 is because 2.5 is a quarter, and on measuring tape that would make most sense to me. We would do 72 feet and 2.25 inches. But again, just for the purposes of this question, just so you kind of get the understanding for the exam or homework question, or whatever the case may be, just box this. Don't kind of be too particular about it. But I'm just kind of giving you the idea that we can do these things. So if this were something that someone was doing in everyday life, you can just calculate real quick to figure out what the amount would be. And if you want to convert it to be accurate enough, otherwise, how do you find, again, 0.2 feet on the measuring tape? It's kind of difficult to do. But 2/4 of an inch is, or 2 1/4 of an inch is definitely on there. Anyways, that's really all I want to say about this. I said I would do a few examples, but to be honest, I think this one is fine enough for us as far as the trigonometry goes. Now I'm going to show an example involving how to find the angle using, again, what I called inverse trig functions, finally. So let's take a look at that right now. Right, so here for an angle theta, again, in between 0 and 90 degrees, not inclusive. Sine inverse, cosine inverse, and tangent inverse are such that if you take these inverse trig functions of their partnered pair trig functions, then you get cancellation and you just get the angle. That's the definition of sine inverse, tangent inverse, and cosine inverse. So, for instance, just to kind of give you this idea, let's say in particular we had triangle ABC, and I guess maybe we should use the notation I've given you before. So let's say it's a XYR instead, and we have this angle theta. Then what is sine inverse, just as an example, like little example, something like IE as example. What is sine inverse of, well, let's see, y over r? Well, since y over r is sine of theta, then we can replace y over r with a sine of theta, so this is sine inverse of sine of theta, like this, and these cancel and you just get theta. So this kind of gives you an example of what this is used for. These are used for when you want to find the angle. Now, as it turns out, you can actually do the opposite. You can take sine of sine inverse and vice versa for cosine and tangent as well. But we're not going to be doing that here. We're going to be solving for the angle, and the angle is inside of the trig function, not the inverse. So it's something kind of technical you could think about if you want. Here I've given us a pretty elaborate example. It's kind of like a long example. To be honest, I don't think we'll have space to do this, so I may have to erase this above. But let's just read this out loud and see if we can get an idea of what's going on and maybe draw a picture to help us out. So it says, an archer aims straight ahead, so 0 degrees, 50 meters away from his target. I should say from his target. Okay. If his shot is not affected by gravity in a significant way, so imagine he shoots his arrow so fast that it doesn't dip down because of gravity, which I guess the closer you are, that can happen. Otherwise, the further you are, you better go really fast. But let's just assume it's a straight shot. Otherwise, we can't use right angle trigonometry. Okay, what angle must he lift his bow by? So he's lifting it just a little bit by a certain angle to land 10 centimeters above his original target. So let's just imagine that I'm going to just draw the bow and arrow like this. And imagine it's going straight, and then we have the target somewhere over here. So let's just say this is the target. This is the board. And then the target's right dead center, let's say. I think that looks okay. So this is a straight horizontal to 0 degrees. Now we want to lift this a little bit, so let me draw that in red because it's kind of like we're moving this a little bit. So he's tilting his bow so that the arrow goes up a little bit. And we want to find the angle such that this new spot where the arrow hits the target is 10 centimeters above. So what we really have is this right triangle scenario, where this is 10 centimeters for the height, and we know the distance is 50 meters because he is 50 meters away from his target. Okay, there's a few things I need to address before we begin. Actually, I guess just one thing. Maybe you can tell right away what it is. It is that they are not the same unit, unfortunately. So we have to do a little bit of conversion. We have to ask ourselves, do we want to keep things in meters or do we want to keep things in centimeters? Now, I say let's keep things in centimeters, actually, because if we write 10 centimeters in meters, it's going to be, well, you'd have to divide by 100, because remember that there's 100 centimeters in a meter, so that'd be, I guess, 1/10 of a meter, which isn't too bad to do, but if you leave this in centimeters, it's actually not too terrible as well. So just to show us with a conversion table, if we have, let's say 50 meters and we want to convert that to centimeters, so let me make that a little more straight. Looks a little better, I think. Yep. Okay. So we're going to divide by meters and we want to get centimeters. Let's recall that there's 100 centimeters in 1 meter. The meters cancel, multiplying across gives us 5,000. So this, let me relabel this as 5,000 centimeters now. Hope that makes it on the screen. 5,000 centimeters. Kind of makes it. Let me tilt this a little bit so we can see that better. Oops. There we go. Sorry about that. Great. So now, of course, now that we're in the same unit, we don't really care about the unit anymore. Now we just know this triangle has opposite side 10 and adjacent side 5,000. And I already said what sides they are. It's opposite and adjacent. So what comes to mind? Tangent, of course, comes to mind. So I'm going to erase all of this. I'm going to draw this picture up here a little more cleanly. And then we'll continue and find the angle in between. All right, so this is where we left off. Now I'm just drawing the triangle here to remove the visualization of what we're actually applying it towards. So we've gotten kind of abstract, but that's fine. Now notice here, they're both in centimeters, like I said earlier. We're going to take tangent of theta. Now when we do that, we get tangent of theta is equal to opposite over adjacent. So it's 10 centimeters over 5,000 centimeters. Notice centimeter over centimeters cancel, so the angle doesn't really matter. Sorry, not the angle. The unit doesn't really matter. In fact, if they were both in meters, we would get the same quotient as it turns out, which is a little weird, but if you do it on your own, if you want to convert this into meters, again, I said it would be 1/10. This would be 50, and 1/10 over 50 actually still reduces to what this reduces to, which you can kind of tell just cancel the 0 on the top and bottom. It's 1 over 500. So really we have tangent of theta is equal to 1 over 500, and now we're going to find theta by taking tangent inverse of both sides. So taking tangent inverse of both sides will do, well, let's see. What does it do for us? Well, it cancels the tangent we have here in place, and it just gives us the angle theta. So now we have our angle theta is equal to this many degrees. So it's tangent inverse of 1 over 500. By the way, I'm expecting this to be a really, really, really small angle. It's going to be in degrees so long as our calculator is in degrees. So let's see if I can do this real quick. By the way, basically all calculators have the same layout as what I'm about to show you. So notice here, I have sine, cosine, and tangent. Also notice if you look closely on top, there's sine inverse, cosine inverse, and tangent inverse. Now to access those, I press second because they're in yellow. So if I press second tangent, that'll give me tangent inverse. Basically every calculator has the same layout. It kind of makes the most sense. Just press the second or shift function, and then those sine, cosine, and tangent buttons become the inverses of those. And that's kind of across the board from every calculator I've seen anyways. And over 1 over 500, or of 1 over 500 I should say, I got 0.11. I want to make sure I'm in degrees. Good. So 0.11459, that rounds to 1146. Let's just round it to, I guess that's fine, 0.1146 degrees, which is super, super tiny. What that kind of tells you is that you better not even move a little bit, because moving just a little bit, that's probably going to be 0.11 degrees, which if you want to think of it, it's like 1/10 of a degree, which is really, really, really precise. All right, so that concludes that example, and that's really all I wanted to say as far as applications of right angle trigonometry goes, for the purposes we need anyways. We'll be seeing more of applications as far as why we need this for greater discussion beyond just what we've seen here. So I'll see you in the next videos for that. Thanks for watching. See you then.